Okay, hello and welcome back. In this video, we're covering section 7.3 on trigonometric equations. So, as the name implies, we're going to practice solving equations that contain trigonometric functions. So we'll use previous strategies of solving more like algebraic equations, and we'll even see some equations that have trigonometric functions but can be solved in a quadratic form. So let's start going through a few examples. So first, let's look at some equations involving a single trigonometric function. In the first example, it asks us if pi over 4 is a solution to this equation. And the equation is 2 times the sine of theta minus 1 equals 0. And in general, if we were trying to find all possible solutions to this, we're trying to find all angles that make this true. And the first thing I would usually do is just solve this equation for this trigonometric function. Just get that on its own and everything else over to the other side. So I would start by adding the 1 over. So I'd get 2 sine of theta equals positive 1. And then divide both sides by 2. So sine of theta equals 1/2. So we can ask ourselves, like, where is this true? For what angles is the sine of theta equal to 1/2? Well, it gives us a couple of suggestions in this question. They ask us, we call this part A, is pi over 4 a solution? Well, let's imagine for the angle pi over 4 that's in the first quadrant, that has the coordinate point root 2 over 2, root 2 over 2. So this has a sine value of root 2 over 2. So I could say the sine of pi over 4 is not equal to 1/2. It does not solve this equation. It doesn't make that statement true. So we'd have to say no. Pi over 4 is not a solution. Then it asks us, is pi over 6 a solution? So pi over 6, that is lower in the first quadrant. Let me add it here. That's 30 degrees. This has the coordinate point root 3 over 2, positive 1/2. So that has a sine value of 1/2. So yeah, if I plug in pi over 6, we would get a statement saying the sine of pi over 6 equals 1/2. It's true. So yes, we can say pi over 6 is a solution to this equation. And I'm saying a solution because I could ask a follow-up of, are there any other angles that make this true? Well, we could imagine all angles that are coterminal to pi over 6. We could just add, we could add 2 pi, we could just rotate around again, 360 degrees, get another angle, which will be different from pi over 6, but has the same sine value. There's also another angle just in one trip around the unit circle over here at 5 pi over 6, which would also have a sine value of 1/2. So this is not the only solution. It's not a unique solution. There's actually infinitely many angles that will make this original equation true. And so we'll think about how to describe all of those possible solutions. But in this case, they give us a single example, one single value, and asks if it is a solution or not. So yes, pi over 6 is a solution to the equation. So let's look at one that asks for the more general solution. This will be example 2. It wants us to solve this equation, and it's already pretty set up for us. Cosine of theta equals 1/2. So where is this true? Let's think just on one trip around the unit circle. Where's cosine equal to 1/2? That's when the x coordinate point, the x part of the coordinate point, is equal to positive 1/2. Well, that happens up here at pi over 3. We get one possible solution. This has the coordinate point 1/2 root 3 over 2. But also down in the fourth quadrant, this has the same x coordinate value. This would be 5 pi over 3, which has the coordinate point positive 1/2, so there's your cosine of 1/2, and negative root 3 over 2. So there's two solutions just in one trip around the unit circle, but then all coterminal angles to that as well. So I'm going to write out what we want. Write it out in words, and then let's convert it to some kind of mathematical expression. So we want pi over 3 and all coterminal angles. And, or I could say or, 5 pi over 3 and all of its coterminal angles. So if you recall a few videos ago when we were trying to describe all of the locations of, say, like the asymptotes of the tangent function, we used some notation, some like general notation to describe an infinite number of values. So let's try to do that same thing here. So I can say theta will equal pi over 3, but I want all coterminal angles, so all possible additions of 2 pi, or we could subtract 2 pi as well, any number of times. So we can say this generally by saying plus 2k pi, 2 pi k, you can move those around if you want, where k is an element of the set of all integers. We can use this general notation, meaning like k can be anything from, going down to negative infinity. We can summarize this as going to like -3, -2, -1, 0, 1, 2, 3. This is the set of all integers. So I'd say k is an element of this. That's what this little e means. It means it can be any one of these things. And that effectively allows us to add any number of 360-degree rotations to our original angle. And we want to capture the same idea for 5 pi over 3. So I can say or theta equals 5 pi over 3 plus 2k pi. Let me just say this statement is true for both of these, where k is an element of the set of all integers. We could use any other letter for k. We could use like n is a common one. I think the text likes to use k, so I'll stick with that. So I would call this statement the general solution. It's the solution that contains all possible angles that have a cosine value of 1/2. So they ask for the general formula for all solutions, and then it wants 8 of these solutions. So some particular solutions. Well, we can get those by starting off, like let's get 4 and 4 from each of these. we can start off with our original angle, pi over 3. The next one would be a distance of 2 pi away from this. So I just want to add some multiple of 2 pi. Well, 2 pi, let's get a common denominator here. If we multiply top and bottom by 3, would be 6 pi over 3. So I could just add 6 pi over 3 and can keep doing that. Every time I do that, I'll get another angle with a cosine value of 1/2. So 1 pi over 3 plus 6 pi over 3 would be 7 pi over 3. That'll be another solution. Add another 6 pi over 3, so 13 pi over 3 plus another 6, 19 pi over 3. So I got 4 solutions. Now let's get 4 from this other statement. We can start at 5 pi over 3. And let's add another 6 pi over 3. So next one would give us 11 pi over 3. Add another 6, 17 pi over 3. Add another 6, we get 23 pi over 3. So we can stop there because we just wanted 8 solutions. But we could keep going. We could list an infinite number. So we have the general solution, and I would call these particular solutions. Like specific solutions to our equation. But in general, we have an infinite number. All right, let's look at another example. So example 3 wants us to solve this equation. We have 2 times the sine of theta plus the square root of 3 equals 0. And this time it gives us a restriction. It says theta is in between 0 and 2 pi. That means just in one trip around the unit circle. So we'll only get a handful of values here. So let's start off just by isolating this trig term. Let's move everything over to the other side. So I'll start by subtracting the square root of 3. So 2 sine of theta will equal negative square root of 3. And then I'm going to divide both sides by 2. So sine of theta will equal negative root 3 over 2. So where is this true? We have to think about, in one trip around the unit circle, where will we have a sine value of negative root 3 over 2? Well, we should be in the third or fourth quadrant, since the sine is negative. And the sine is root 3 over 2 on these like pi over 3 angles. So there's one down here in the fourth quadrant. That would be 4 pi over 3. This has the coordinate point negative 1/2 negative root 3 over 2. And then there's another one in the fourth quadrant. This would be 5 pi over 3, which we saw from our last one. This has the coordinate point positive 1/2 negative root 3 over 2. They both have a sine value of negative root 3 over 2. Oh, and this was 5 pi over 3. So we do technically have an infinite number of solutions here, but it just wants in one trip around the unit circle. So let's just list these two angles. I can say theta will equal 4 pi over 3 and 5 pi over 3. We get 2 solutions. So just take note, if they give you a specific interval where they want you to list all values on that interval, it's common to just go once around the unit circle, but they might ask you something beyond that too. So just take a note there. All right, let's look at one that's a little bit more complicated. It says solving a trig equation involving a double angle. Let's look at how this one would be different. we're given the sine of 2 theta equals 1/2. And they're saying theta is between 0 and 2 pi. Well, notice now we have not just theta inside, but 2 theta. So we have to, this will complicate things a little bit. It can be useful to do a substitution to think about this a little bit differently. Like I'm going to say, let this random variable u equal 2 theta, that thing that is inside here. So this is mostly for like a visual help to help us think about this. So I can re-express this as just the sine of u equals 1/2. Just some angle, because that's ultimately what this is. We're going to ultimately have to solve for specifically theta instead of 2 theta. But let's just first think in general, where is the sine equal to positive 1/2? Well, imagine the unit circle. The sine is positive 1/2 at pi over 6. This has the coordinate point root 3 over 2, 1/2. And then also over here in the second quadrant at 5 pi over 6. This has the coordinate point negative root 3 over 2, positive 1/2. They both have a sine value of 1/2. So these won't be my solutions because this would be for u, which is 2 theta. But let's just think what would be the general solutions here in terms of this substitution we made in terms of u. And let me keep with this blue color just to help us. Keep in mind, like this is a substitution. We're going to have to undo this substitution eventually. But I can say u is equal to pi over 6 and then plus all coterminal angles, plus 2k pi. Or we have our other angle. I can say u equals 5 pi over 6, also plus 2k pi. And this is where k is any integer. But let's keep in mind that this thing, u, equals 2 theta. So let's undo this substitution. I'm going to look at this first statement. So instead of u, I will say 2 theta equals pi over 6 plus 2k pi, where k is any integer. And we're trying to ultimately solve for theta and not 2 theta. So let's divide everything by 2. Then we'll get that theta equals pi over 6 divided by 2. That's like multiplying by 1/2. Pi over 12. And then we have to also divide this term by 2 as well, this like general term. We have 2k pi divided by 2, and we'll just get k pi, some multiple of pi. So like 1 pi, 2 pi, 3 pi, 4 pi, or also negatives as well. So we can also see that as like 12k pi over 12 to imagine a common denominator. So we want to produce all solutions here in this interval from 0 to 2 pi. And it might be helpful to get a common denominator of 12 just to know when we've gone too far. You can say 2 pi is equal to 24 pi over 12. So I want to list all possible solutions, or all like particular solutions from this general statement that fall within that interval from 0 to 24 pi over 12, which is equivalent to 2 pi. So our first one definitely falls in that range. We can say this would equal to pi over 12 if k is equal to 0, just that first angle. And then if we add k pi, or we can say add another 12 pi over 12, then that would be 13 pi over 12. And that's less than 24 pi over 12, so that would be another solution. If I add another 12 pi over 12, so add another pi, that would push us beyond 24. We would get 25 pi over 12. Let me just write that out, just to be sure. If we have 13 pi over 12, and we want to add another pi, so 12 pi over 12. Yeah, that would be 25 pi over 12, which is beyond 2 pi. So we'll have to stop there. So that was our first statement. Now let's look at this second statement that we had here. We said u equals 5 pi over 6 plus 2k pi. So let's replace u with 2 theta. This will equal 5 pi over 6 plus 2k pi. Let's divide everything by 2 because we're trying to solve for theta. So this will give us 5 pi over 12 plus k pi. It's another multiples of 12 pi over 12 to get a common denominator. So we'll get our first solution, 5 pi over 12, when k equals 0. And then when k equals 1, it's a similar thing to what we did before. We would be adding pi, adding 1 pi, which we can express as 12 pi over 12. So that will give us 17 pi over 12, which is less than 24, less than 2 pi, so we can have that as another solution. And then if we added another 12 pi over 12, we would be beyond 24 pi over 12. So we get two solutions, two particular solutions from each of these statements. So let's combine it together into a single solution set. I'll say theta equals, we have pi over 12. I'll try to go in order. We have 1 pi over 12. Over here we had 5 pi over 12. Then we have this 13 pi over 12. And then the 17 pi over 12. So we get these four particular solutions between 0 and 2 pi. So let me just summarize because these end up being a little bit more tricky. We have some statement like this, where instead of just theta inside, we have something more complex. In this case, we have 2 theta. We could have anything could be inside of there. There could be something added or subtracted or multiplied or divided. So for me, it's helpful to do this substitution where I think just in generally, where is the sign of something equal to 1/2? So I do this, I call it a U substitution. We could have just kept this as 2 theta the whole time, but this can be a visual help to get us started. So the sign of something equals 1/2. Well, we can find around the unit circle where that's true. And then we build this general solution for each one. So each of those points, or each of those angles, and plus every coterminal angle, that's 2k pi. Then I undo the substitution. So I'm remembering u equals 2 theta. So I get the same statement, but replace it with what was originally inside. In this case, it was 2 theta. And then solve this general statement for theta. So you have to like add or subtract or divide over. In this case, we had to divide 2, everything by 2. And then you get these general statements. So you want to go through possible solutions here and collect all of them that fit in the given interval that they're asking for. In this case, it was between 0 and 2 pi. So you start out with your first term, So imagine k equals 0, it just deletes that second term. You get the first one, so that gave us our first solution. Then I added, when k equals 1 pi, so 12 pi over 12. That gave us our second solution. Then I just keep adding those until I fall outside of the interval that they're asking for. And then we did the same thing for our other solution too. So these are a little bit more tricky due to having something more complicated inside of the trigonometric function. So let's see, I think we get another example here. Yeah, let's look at another one. So notice we have that same situation. We have the tangent of theta minus pi over 2 equals 1. And theta will be between 0 and 2 pi. So we have something more complicated than just theta. If this was just the tangent of theta equals 1, we can list out where that's true around the unit circle. So I'm going to do another substitution. I'm going to say let what's inside of this function equal u. And again, this is just a visual help here. It lets me know I'm looking for where is the tangent in general, the tangent of something, equal to 1. Well, that's true for some of our pi over 4 angles. Like at positive pi over 4, that has the coordinate point root 2 over 2, root 2 over 2. So sine divided by cosine, which is our tangent, will give us positive 1. And we get another solution in the third quadrant at 5 pi over 4. This has the coordinate point negative root 2 over 2, negative root 2 over 2. So when you divide those, the negatives cancel, and we also get a tangent value of positive 1. So those were the two places around the unit circle where just in general the tangent is equal to pi over 4. So let's build our general solutions. I would say u equals, let's look at this first one, positive pi over 4, but then plus all coterminal angles, so plus 2k pi, where k is an integer. So let's go ahead and find our solutions from this one version. Let's undo the substitution. Instead of u, I'll say what was originally inside of the tangent function, theta minus pi over 2 equals pi over 4 plus 2k pi. So here, we want to solve for theta, so I'd be adding pi over 2 over. I'm going to add pi over 2, it's going to add to this pi over 4. Let's think about what that would be. I'm going to have pi over 4 plus pi over 2. Let's get a common denominator. So that would be 2 pi over 4. So it would be 3 pi over 4. So solving for theta, if I added that pi over 2 over, it combines with the pi over 4, and I get, oops, I wrote a 3 here. I would get 3 pi over 4 plus 2k pi. So 3 pi over 4 plus 360 degrees. And we want to be within 0 to 2 pi. So we should only get this as our one solution from this statement. 3 pi over 4. Because if I add 2 pi, like when k equals 1, I'll be beyond 2 pi. So we get one solution there. All right, let's look at our second general solution, because we said tangent was also equal to 1 at 5 pi over 4. So in terms of u, I would say u equals 5 pi over 4 plus 2k pi, so all coterminal angles. And then let's undo the substitution, because we said u was equal to theta minus pi over 2. And this will equal 5 pi over 4 plus 2k pi. So just like last time, we'll have to add the pi over 2 over. So it'll combine with the 5 pi over 4. So 5 pi over 4 plus 2 pi over 4, that's our pi over 2, would be 7 pi over 4. So theta will equal 7 pi over 4 plus all coterminal angles. Or plus like all multiples of 2 pi. So all coterminal angles to 7 pi over 4. So we'll get our first solution is the 7 pi over 4. If we imagine k is equal to 0. And then if we add 2 pi to that, when k equals 1, we'll be beyond our upper bound. So just like last time, we'll just take that first value. So let's go ahead and write our solution set. So we'll get this 3 pi over 4, and then our second solution will be the 7 pi over 4. I'll build a little solution set. I'll put these two in. And this will be our two solutions between 0 and 2 pi. So in this case, we didn't get any like additional solutions like last time. We just had our two base ones. So again, just to summarize, we went through the same process. I use this substitution method. You don't technically have to do this. You could just, you would still ask yourselves the same question, whereas just in general, the tangent equal to 1. You would still imagine these two angles and then end up with statements like this. It's helpful for me to do this substitution, so kind of an extra step. But that's what we're doing. We're asking, where is the tangent equal to 1? Well, that's true at pi over 4 and 5 pi over 4. So we built these two general statements. Pi over 4 plus all coterminal angles, 5 pi over 4, and all coterminal angles. Then I undo the substitution, so replace it back with what was originally inside of the trig function. And then solve for theta and see which of these particular solutions fall within our interval. And we did the same for our second statement. So it takes a little practice to get the hang of this process, but once you get it, it feels a little bit more simple. But there's sort of two phases. This general, again, general, where is the trig function equal to this value? And then you have to do a little bit of rearranging to solve for theta, because ultimately we're trying to find all theta values that make this true. Okay, our next section is on solving trig equations that are in quadratic form. So we'll see what that means. So let's recall a quadratic is something in the form ax squared plus bx plus c equals 0. And notice we have a squared term and a term to the first power, and maybe there's some coefficients, maybe some constant term. And how have we solved these in the past? Well, either by factoring, by applying some factoring methods, or by using the quadratic equation. So we'll be using those same methods here. There'll just be some trig functions involved. So let's take a look at our first example. We have 2 sine squared of theta minus 3 sine of theta plus 1 equals 0. So notice we have that same kind of setup. We have something squared and something to the first power. Now instead of x, it's the sine function. But we can still apply quadratic methods. And I'm going to do another substitution here. Again, this is just a visual aid. I'm going to say let u equal the sine of theta. It's not fully necessary, but this can be helpful, especially in the beginning as we're getting used to this. So that would transform this original equation into 2u squared minus 3u plus 1 equals 0. You could even use x too. I could say let x equal sine of theta. You get 2x squared minus 3x plus 1. This might help you recall how to solve something like this. So we want to do some factoring. So we have a leading coefficient here in front of the squared term. So I'm going to do what I've called AC method factoring. It might be called different things depending on what you've learned in terms of algebra. But when I say AC method, I'm referring to, in this general form, we usually call this coefficient A and then this constant term C. So I start with multiplying those two. So 2 times 1 is 2. And then I think of two factors that add up to this number, or that multiply to 2, that add up to my constant term. So what would that be? Oh no, I'm sorry, I said that a little bit wrong. I need two numbers that multiply to equal this number. So two factors of 2 that add up to my middle term of negative 3. Yeah, I said that a little bit wrong. So, well, that would be negative 2 and negative 1. Negative 2 times negative 1 equals positive 2, and negative 2 plus negative 1 equals negative 3. So I'm going to rewrite this middle term using these two numbers. I'll show you what I mean. So 2u squared. So I'll say instead of minus 3u, I'm going to say minus 2u minus 1u. Then we still have the plus 1 equals 0. And then now I can factor this by grouping. So I can imagine two groups here. Let me first put them in groups. I have 2u squared minus 2u. I'm going to stick a plus in the middle, and then I have minus u plus 1 equals 0. So recall in factoring methods, now we factor as much as we can out of each of these two expressions. So in the first one, I can pull out a 2u, and I would have u minus 1 left over. And remember, with factoring by grouping, I'm trying to produce the same factor over here as well. So here I have negative u plus 1. So if I factor out a negative 1, that will turn this into positive u minus 1. So factor out a negative 1. Then we have this common factor of u minus 1. So that gets factored out of this total expression, and we end up with our common factor of u minus 1 times our second factor would be these two coefficients, 2u minus 1. Alright, so we're using a little bit of algebra skills, which we may not have done for a little while since we've been focusing so much on trigonometric values. But we're ultimately just factoring a quadratic to solve. But we're not done there. Make a little more room. We need to solve each of these separately. So two factors multiplied equal to 0. We can set them separately equal to 0. So u minus 1 equals 0, and 2u minus 1 equals 0. Solve these for u. U equals positive 1. The second one would give us 2u equals 1, and then divide by 2, u equals 1/2. But let's remember what u was. We said u was the sine of theta, so we need to undo this substitution. So let me jump up here. You can say, instead of u, I will say the sine of theta equals 1. or the sine of theta equals 1/2. And remember, we were asked for this interval. We want all values of theta between 0 and 2 pi that make these two statements true. So now we have like two little trig equations to solve. So between 0 and 2 pi, that's one trip around the unit circle. So what are all angles that have a sine value of 1 or 1/2? Well, for 1, that would be at pi over 2. Sine is equal to 1 there. That's the 0.01. And sine is equal to 1/2. We've seen that one a couple times now. That's at pi over 6. And then also in the second quadrant at 5 pi over 6. So we get three solutions between 0 and 2 pi, just one trip around the unit circle. So let's create a solution set. Let's say theta equals pi over 6, pi over 2, and 5 pi over 6. So we get three solutions here. So this was a trigonometric equation in quadratic form, and that would be the first thing to recognize. We have something squared and then something to the first power, like ax squared plus bx plus c equals 0. So we can solve it as if we were solving a quadratic equation in x, like we've done previously in algebra, just instead of x, we have a trig function. So I've used this substitution method. In our next example, we'll try just keeping the trig value. The process is the same. But doing a substitution can help you visually, it might visually help you see, okay, I have a quadratic expression. I need to solve it by factoring. And then once you get to this point, if this was just x, this is usually where we would stop. We'd say like x equals 1 or x equals 1/2. But in this case, we have a trig function, so we need to ask what angles make these two statements true. And they usually give you some interval. We could have a general solution as well, but a lot of times they like to say between 0 and 2 pi, like in one trip around the unit circle. All right, let's look at a couple more. So notice this is saying solving a trigonometric equation using identities. So let's keep in mind some trig identities we've seen previously. So let me write out our equation. We have 3 times the cosine of theta plus 3 equals 2 sine squared of theta. So what can we do? Notice we have sine and cosine both present in this equation. So a general strategy is to try to express everything and try to express your equation all in terms of a single trig function. It's more complicated when we have multiple trig functions like this. So what can we do? And we have the hint of using an identity. So I see the sine squared, and recall we had that Pythagorean identity sine squared of theta plus cosine squared of theta equals 1. And we defined that back when we were building the unit circle. So notice if we solve this for sine squared, like let's subtract everything else over, we get this statement sine squared of theta equals 1 minus cosine squared. Meaning we can replace this sine squared in the equation with 1 minus cosine squared. And then we would only have the cosine in our equation. And that's what we want to achieve. So let's do that. Let's replace that sine squared with 1 minus cosine squared. We could do the same thing if it was a cosine squared. We could solve this for cosine squared. So we can get a similar statement that cosine squared equals 1 minus sine squared of theta. So these all become useful. They're kind of different variations of that Pythagorean identity. So notice we have a statement now. We have cosine to the first power and cosine to the second power. So we can ultimately express this in quadratic form. Let's get everything moved over to the left side and equal to 0. So I'll start by distributing that 2. So 3 cosine theta plus 3 will equal 2 minus 2 cosine squared. And then I will add that 2 cosine squared over to the other side. So I'm going to put that in front. It'll appear as positive 2 cosine squared theta. We have the plus 3 cosine theta. And then I'll subtract that 2 over, so we should get plus 1 at the end. And it will be now equal to 0. So at this point, we could do another substitution and get like 2u squared plus 3u plus 1 equals 0. Let's try just keeping the trig functions in there, just recognizing this is in quadratic form. Just to give it, I just want to show an example of not doing the substitution, but you're welcome to choose whatever method is most helpful for you. So I'm just going to imagine this is like my x squared and this is my x, and I'm going to just factor this as a quadratic. So I'll do that same AC method. 2 times 1 is 2, and then factors of 2 that add up to positive 3 are 2 and 1. So that's how I want to rewrite my middle term. 2 cosine squared of theta plus 2 cosine theta plus 1 cosine theta plus 1 equals 0. So I'm splitting that middle term into these two terms. Then I can factor by grouping. So I'm imagining this is in one set of parentheses and this will be in my second set. So in the first set, they both have a cosine and they both have a 2. So I'm going to factor out 2 cosine of theta. And what would be left over? I took the 2 and I took 1 cosine, so there should just be 1 cosine left. And from the second term, I took 2 cosine theta out, so there should just be a plus 1 left over here. And then my second factor is already cosine theta plus 1. There's nothing else I can take out of that. And it's already this common factor that I have. So the next step is to write the common factor. So we're factoring that out of this total expression. So I have the cosine of theta plus 1 in parentheses, and my second parentheses will be my 2 coefficients here. So the first one is 2 cosine theta, and the second one would be plus 1. So setting these separately equal to 0, I can say cosine of theta plus 1 equals 0, or 2 cosine theta plus 1 equals 0. So now I have two little trig equations. So let's solve each of these for the cosine. I'll subtract the 1 over, so cosine of theta equals negative 1. Or here I would subtract the 1 and then divide by 2. So we can say cosine of theta equals negative 1/2. And our question was asking for theta values between 0 and 2 pi again. So in one trip around the unit circle, where is the cosine equal to -1 or -1/2? So let's imagine. And then that will give us all of our solutions. The cosine is equal to -1 over here at pi. That has the coordinate point -1, 0. And the cosine will be equal to -1/2. We get two solutions. The first one is our pi over 3 angle in the second quadrant, so 2 pi over 3. That has the coordinate point -1/2, positive root 3 over 2. And then we get a similar one in the third quadrant. So this would be at 4 pi over 3. This has the coordinate point -1/2, negative root 3 over 2. So they both have the cosine value of -1/2. So we get these three solutions in one trip around the unit circle. So I'll say theta equals 2 pi over 3, also pi, and also 4 pi over 3. We get three solutions here. So this one was a step in the, like a little bit more tricky. We started off with two different trig functions in our equation. So a general strategy is to try to express everything in terms of a single trig function. So we used this Pythagorean identity. We had to modify it a little bit, but if you see a sine squared or if you see a cosine squared, you can always turn that into the other, like you can turn a sine squared into some expression with cosine using this Pythagorean identity. So we replaced sine squared with 1 minus cosine squared. And then from then on, we're just solving it like a quadratic until we get to this bottom part where we need to then reference the unit circle and find what angles make these two statements true. So I did this one without doing a substitution, but we could have done that at this point. I could have said let u equal cosine, and we would get something like 2u squared plus 3u plus 1 equals 0. Or you could use x or whatever variable you want to choose. And if you prefer that, and then solving that like a quadratic, and then undo the substitution at the end, sometimes that can be helpful, especially as we're getting used to this process. Okay, let's look at one more example. We have here example 9. So we want to solve cosine squared plus sine of theta equals 2. So let's use that same idea. I want to get everything in terms of just the sign. We have cosine squared. Let's remember sine squared plus cosine squared equals 1. It's a really useful identity that comes up in a lot of contexts. And then if I solve this for cosine squared, I can say cosine squared of theta equals 1 minus sine squared. So let's replace this cosine with 1 minus sine squared. So 1 minus sine squared theta plus the sine of theta equals 2. So let's get everything on the left side equal to 0. So I have like negative sine squared theta plus sine of theta. I'm subtracting that 2 over, so 1 minus 2 would be -1. But let's get the leading term to be a positive 1. Let's multiply everything by, oh, and sorry, this should say just -1. Let's multiply everything by a -1. So that'll make this positive sine squared of theta minus sine of theta plus 1. We can imagine just adding everything over to the other side. So at this point, I would try to factor. I'd be thinking of factors of +1 that add up to -1. So there's nothing that'll make that true, which is an indication that we should use maybe the quadratic equation to try to solve this. Here it's useful to view this as a substitution. I'll say let u equal the sine of theta. So then we can view this as u squared minus u plus 1 equals 0. So since we can't factor this normally, let's use the quadratic equation. So just as a reminder, if you have quadratic, ax squared plus bx plus c equals 0, there's the equation x equals -b plus or minus the square root of b squared minus 4ac over 2a. So in this case, our a is 1, our b is -1, and our c is 1. So we could say u equals -1 plus or minus the square root of -1 squared minus 4 times 1 times 1 over 2 times 1. Well, notice what's going to reduce under the square root. This would end up becoming +1 plus or minus the square root of, that'll become +1 minus 4, or we could say -3. So we have a negative number under the square root. So there's going to be no real solutions here. And at this point, we'll have to stop because we're not doing anything using imaginary numbers, at least not yet in terms of trigonometric equations. So we'll have to say no real solutions. Definitely no solutions between 0 and 2 pi, which are real numbers. So at that point, we'll have to stop here. So if you have to do this using the quadratic equation and you get some negative number under the square root, there will be no real solutions. So keep an eye out for that as well. So we saw these get increasingly more tricky, especially this last one, example 8, where we had to use an identity. And you may see some other examples where you might have to use some other kinds of identities, so it might be good to review what we've seen so far in terms of trigonometric identities. And then if you're a little bit rusty with the algebraic techniques, so say with factoring, it might be worth revisiting factoring quadratic expressions, because there's a few different situations you might run into. So in general, with trig equations, we might have something more simple like we saw originally, say like with these examples. We just have a single trig function. Usually you just have to isolate that and then solve for theta. Or they might be in quadratic form or something that might involve some kind of factoring technique. So just keep that in mind as you work on the homework exercises. Try to recall some algebraic techniques of solving equations, and those will apply here as well. All right, that's it for this video. So we solved quadratic equations involving a single trig function. I did not include solving using a calculator. We're doing everything, we're focusing on these techniques, doing it by hand here. So if you're interested, you can view that in the textbook. We solved quadratic equations in solved trigonometric equations in quadratic form. And then we also solved trig equations using fundamental identities. There's also another section in the textbook solving using a graphing utility. So in some applied questions, you might just want to graph the equation and try to solve from there. So you may want to check that out too. But I would focus on these three parts of the textbook section. Okay, that's it for this video, and I'll see you next time.